Welcome in, everyone. We're going to go ahead and get started with threesome today. Okay, so let's take a look. We'll read the problem. We will talk through the naive solution for just a moment, and then we will optimize it a little bit. Okay, sweet. All right, so let's read through it. It says, given an integer array nums, we want to return all the triplets, nums I, nums j, nums k, where the sum of those three values is equal to 0, and then also the indices I, j, and k are all distinct. And so that's another way of saying we can't use the same entry of the array multiple times. And then the output should not contain any duplicate triplets, and we may return the output and the triplets in any order. Okay, so let's actually just go back for a sec just to make sure some of those entry pieces of information are clear. So when they say that I, j, and k are all distinct, this means we have to use separate entries of the array, but those entries might be identical. So if the entire array is zeros, for example, we've got 5 zeros, let's say, we can actually return 0, 0, 0 because there are more than, or 3 or more zeros. So it's totally fine to have repeating numbers, we just can't use the same actual entry or the same index multiple times. And then notice also what we're going to return is the triplets that are the actual values. So these are not the indexes of the array, but instead these are the numbers in the array that sum up to 0. Okay, so for this example array here, we got -1, 0, 1, 2, -1, -4, and the triplets that we return are -1, -1, +2. If you add those up, hopefully you get 0. And then -1, 0, 1, again, hopefully you add those up and you get 0. Hey, welcome in, folks. We are looking at threesome, in case you missed it. Okay, so yeah, notice in this particular array, not sorted. We can sort it if we'd like, and in fact, that's something that we'll do, so I'll just talk through that in a sec. The next example here, they give us 0, 1, 1, and the output is an empty list, and this is because there's no elements that you could pick here where all three of them, or the sum of the three adds up to 0. The only way you could do that is if you chose 0 3 times, but again, since we need the indices to all be distinct, we can't do that, so we can't repeat this element. If it was 0, 0, 0, 1, 1, we'd be good to return 0, 0, 0, but that's not the case here. Okay, and speaking of 0, 0, 0, we return 0, 0, 0, and that's because 0 plus 0 plus 0 is, you guessed it, 0. Okay, so some constraints that they give us. The length of nums will be between 3 and 1,000, so it could be lots of numbers here. And then the numbers themselves will be between -10 to the 5th and +10 to the 5th. Really, this is just to assure us that we're never going to deal with like integer overflow or anything like that. So reasonably sized numbers, 3 to 1,000 of them. So let's think about it. Let's actually take their sample array here because I think it's a pretty good one. -1, 0. Let me split my screen here. Okay, we've got -1, 0, 1, 2, -1, and -4. Okay, so how could we solve this naively? Let me go ahead and actually close this out. Come back to it later. So how could we solve this naively? Since we need triplets, what we could do is we could have kind of an outermost index or pointer here that just goes one by one through the array. So we'll basically say, like, let's say this is the first element of the array. And we could try and pair it up with the things that follow it. So we could say, okay, let's consider this triplet right here. Does that add up to 0? It actually does by chance. So, you know, right off the bat here, when we initialize these three index pointers, we can say, hey, actually, one of the things we can include is -1, 0, 1. And then we could check against all of the possible combinations here. We could check -1, 0, 2, -1, 0, -1, -1, 0, -4. And then we would slide this guy over and start it again, -1, 1, 2, which actually is, nope, just kidding, -1, 1, -1, -1, 1, -4. And we would just keep doing this for the naive solution until we tried all of the possibilities. And this is actually our next answer here, which is -1 to -1. Ooh, I just killed a mosquito. That's crazy. All good. -1 to -1. And we would just repeat this. You know, we would cycle through until these guys got to the end. And then once these guys got to the end, we would move this guy over here and consider all the possibilities. Does anybody want to hazard a guess to the time complexity of doing this process here? O of what's the name of that emoji? O of smile emoji. Yes, it is correct. This is n cubed. So for every entry, and again, well, we've talked a little bit about how we can generalize this, but for every entry that the red guy looks at, we're going to look like every one of these guys. This guy's going to move all the way through, and then for each of those, this guy's going to move all the way through. So we've got n times n times n, right? Okay, now the optimal solution is actually not vastly better than this. In fact, if you want to solve this the naive way, which, if you want to give it a shot, that actually is sometimes a good place to start your code, is just with any solution at all. The last thing that you really have to look out for here is what if you have duplicates. This one doesn't have any duplicate entries, but if some of these numbers repeated themselves, how are you going to make sure, for example, that you don't also return 1, 0, -1? Because according to the constraints of the problem, we only want distinct triplets. So these are the same triplet, just in a different order. So we're going to have to figure out some way, if we do the naive solution, of deduplicating those. Okay, but there's a little bit of a better way for us to handle this. So remember, our baseline here is an O of n cubed time complexity. We're trying to improve that. We're actually not going to get super far. As I understand it, the optimal way to solve this problem is at an O of n squared time complexity. So it's better, and for huge data, it's a lot better. But because we're looking at n cubed, n squared time complexity, it's not a bad idea at all to say maybe we should sort the information first. Hopefully you recall from our previous sessions that sorting, we tend to say that it falls in the realm of O of n log n, which, wow, let me actually just compare this for our people who have maybe not studied time complexity a ton. If we're comparing these, n cubed, right, is n times n times n. Oh, hello. N cubed is n times n times n. N squared is n times n. And then when we say n log n, if we were to directly compare these, the n's match up, but the log n is smaller, right? So n log n is better than n squared, worse than n. But because of that, if we decide to sort this, we're not worsening the time complexity. We're just sort of doing an operation that is on par with the rest of the problem that we're going to solve. So totally reasonable for us to want to sort here. There's actually a really good reason for us to do that. If you were around for twosome, you may recall that one of the difficulties that we had was, since the data wasn't guaranteed to be sorted back then, we had to go through and spend some extra space and some extra logic figuring out if we had seen certain numbers before. So, excuse me, if we sort the numbers instead, we can be a lot smarter about this because, and let me just focus my brain power on writing this real quick. We can be a lot smarter about this because if we want to make certain combinations, in this case combinations that sum up to 0, we can look at essentially a pair of numbers and know which, wow, how do I phrase this? We can know what changes we need to make to get a better combination. So here's what I mean by this. If we are considering -4 as the first element, right, of this hypothetical triplet, if this does make a triplet, then if we look at these, the next two things, well, first of all, we can, instead of just looking through the entire array, n squared times, we can initialize 2 pointers that look like this. And when we add those up, all three of these numbers, we're going to get something negative, right? -4 plus -1 plus 2 is going to be -3. Since our target is 0, we know that we want to choose numbers that make the sum bigger, right? So if we have -3 and we want 0, we need to increase that sum somehow. If we know that we want -4 to be one of the elements, then we need to manipulate these guys somehow to make a smarter decision about getting closer to 0. Well, let's think about this. Since these are the bigger numbers, these are the smaller numbers, if we move this guy in, the sum is going to get even smaller than it was before, right? If we were already at -3 before and we get even smaller than that, this is going to take us to -4 as the sum. That's not helping us get triplets that we want, right? So in short, if we add these up and the sum is negative, we want something bigger, we're going to take this left pointer and move it over. In this case, it's the same number, it doesn't improve at all, so we move it over again. Okay, now if we add these three numbers up, we get -2, still too small, so we'll move this over. Now it is -1, and that's it. Now that the left pointer is going to meet the right pointer, that's not something we're allowed to include in our answer set, so we can say, okay, this exhausts all of the possibilities where -4 is the first number. Okay, and notice, because of the way that we looked through the data here, we didn't have to look, only one pointer moves at a time, right? And so because of this, for this element, at the very maximum, we're going to look through every other element once, right? And then we'll stop. So if we do that for all n elements, that's n times n, or n squared time complexity. So just for the sake of getting at least one match here, now that we've exhausted all the possibilities that start with -4, we can try some of the possibilities to start with -1. Again, our other 2 pointers will be kind of at the start of the interval and the end of the interval. -1 plus -1 plus 2 is actually equal to 0. So this is part of our answer set. And here's one of the nice things about doing the sorting is if we decide to sort, we're guaranteed that we're always going to have these numbers in order, right? So we won't have a situation, for example, where we also try and put in 2, -1, -1. That's not something we have to worry about. Okay, so that's one of the nice benefits of using sorting here. And then here's the other thing. If there was, let's say, another -1 in here, well, okay, sorry, that was a strength of the sorting method. Let's say there was another -1 in here, though. One thing we have to watch out for is when we move this guy over, for example, we might think that this should be another part of the answer. In reality, this is another duplicate, right? Because we've already seen -1, -1, 2. Hopefully, again, by now, you've done a few of these problems and you're aware that sets are a data structure we can use to avoid that duplication. So that's what we'll do. Anyways, okay, so what happens when we get a match? When we get a match, what we need to do is basically say, like, we can't use these numbers anymore, but there's still a possibility that there's other things that work the way we want them to. So let's rewrite the data here. Maybe this is a, ooh, actually, let me think about this. Oh, no, actually, yeah, we're actually going to see another combination. So just because we found a match doesn't mean we're done. In this case, when we find a match, we can move these guys in. Right, because now that this is a match, we're never going to need those two numbers again. If we only move one of them, we're guaranteed either it's the same combination or it's not actually the correct sum. So we'll move both of these in by 1. And notice the red pointer is still in the same place. This is going to be another solution. So just because we get a match doesn't mean we're ready to move this guy over. We actually want to continue looking inward until we've exhausted all the possibilities. So in this case, we get another match. I'm going to go ahead and record this. It's -1. Oh, wait, this isn't a match. Just kidding. So this isn't a match. -1 plus -1 plus 1 is -1, right? Which is smaller than we want it to be. And so since it's smaller than we want it to be, we're actually going to move the left pointer over to increase the sum, right? Am I recording now? God, I hope so. Yes, I am. Okay, so again, we'll just very quickly recap here. We get a match here, this equals 0, so we move both of these in by 1. The sum is too small, so we move the left pointer up, and now we actually get another match, so -1, 0, 1. Again, what's nice is we're guaranteed that this will be sorted. And now that we know that it's a match, we can move these guys in. So this will go over here, this will go over here, and now that they've crossed paths with each other, which again is the part of the 2-pointer approach, we can say this means we're done. We've already looked at these combinations. We're now just going to start getting them in reverse order, which we don't want. So we're ready to swap this guy over, move these to the ends of the following interval, and repeat the process again. We know, since we've done this a few times at this point, that there's no other combinations. Oh, I forgot I added that -1. Well, there's no other combinations that will work that are unique. So when we look at this one, we could see that this is -1, -1, 2. Well, we've seen that already, so the set is going to handle that, and we continue the process from there. So in short, the logic is sort the numbers, have an outer pointer that is going to go, and that's this one, an outer pointer that is going to check each of these numbers once, And for each of those numbers that we check, we can adjust the left and right pointers on the following interval based on whether the sum is too small or too big. There's a couple other optimizations we can make, but we'll start with that just so we can like get a solution down, and then we'll do some tweaks. We'll add a little bit of extra stuff. Any direct questions so far on the approach as I swap over to writing the code? Oh, brother, what does this guy have to say? Oh, what's the question? I'm so curious. Is there an actual question in there? What's a practical application for this? That's a great question. A practical application would be getting you a job. To be fair, a lot of LeetCode problems are more tested at like kind of probing your critical thinking skills and your problem solving skills. So the thought is, this is really about analyzing, what is, well, like for example, now that we've sorted the numbers, we can make a smart decision, right, about how to move those pointers that helps us in terms of efficiency. So the thought, and I don't know if I totally agree with this, but the reason why we get asked these in technical interviews is because there's supposed to be some indicator of whether or not you pick up on patterns, how you approach things that can be optimized, whether you notice, that there are smart decisions you can make about your programming efficiency. So the problem itself, there might be something in here about like team matching perhaps. So like if you had a bunch of people who were ranked in a certain way and you wanted them to be formed into fair teams, you might give them ranks and then make sure that those ranks all add up to 0, right? So if you have an especially unknowledgeable person, an especially knowledgeable person, and then somebody at the baseline, that could be an example of where this comes into play. But not all of these problems will have applications like that. So this is one of them that's just kind of like, I don't know, you could probably like push it into a situation, but yeah. All right, so let's take a look at how to actually code this. I'm actually going to side-by-side this with a diagram. Of course, Dave, anything for you. Okay, let's move this all in here. Okay. So, what are we going to need here? We're going to need a results data set or data structure here. I'm going to make it a set because, again, we kind of like that it handles the duplicates for us. We might need more than that, but we'll start getting going here. So I'm going to use a trick that we've used before for iterating over each element of an array. Since we want the index, so we can initialize those other pointers, and we also want the number itself, we can say for index and value in enumerate nums. So this is going to get us, we're going to go through each element of the nums array, and we can refer to the index by index and the thing at that index as value. And again, these are arbitrary names. I could have named these like I and V, but we like, for the sake of interviews, expressive variables, right? If you're collaborating with other programmers, hopefully they can look at your code and know what it does, right? So we want to avoid nonsense, gibberish, one-letter variables when we can. Okay, so for index and value in enumerate nums, what exactly are we going to do? Okay, so this right here is our red pointer, right? The first thing we need to do in terms of the overall algorithm here is we want to say, okay, let's say we have left and right. These are going to be the green and blue pointers. Left, when we start this loop, is going to start, and actually I'll move these around a little bit. Left is going to start right next to red, right? And then right is going to start at the end of the array. So when we initialize these, we want something like index plus 1 and the length of nums minus 1. All right. Well, actually, let's think about this real quick. We don't need to do the... Well, I don't want to over-optimize it first. Let's get through the overall algorithm, and then there's things we might change. One thing I'm thinking of, though, ahead of time is if we do this for everything, we're just going to want to make sure that we have valid indices at the end here, right? So if red is at the very end and we try and make left 1 to the right of that, that might cause us problems. So I'll keep that in mind. We haven't done anything that causes that problem yet, so we'll take a look. Okay, so here's what I'll say is the overall algorithm says that while left is less than right, we're going to do some checking, right? So I'll say that the 3 sum, which again is just the addition of these 3 numbers, is going to be the value we're currently looking at as the first index, as the first element of the triplet, plus the nums at left plus nums at right. Okay, so far I'm already seeing if, for example, this was, well, we're guaranteed this isn't going to happen, but just for the sake of illustration, if this was a 1-element index or 1-element array, this would immediately cause problems because left is supposed to be 1 over, right? So if we now try and add in nums left, well, okay, no, but that's not going to happen because these are going to be the same place. So let's say it's a 2-element array. In that case, no, oh god, actually, the 2-element array isn't going to do that either, huh? Well, there may be a place where this causes problems. I'm just going to think about that for a sec. Yeah, I think all of the places where this can happen, this part will never actually run because left and right will be the same as each other. So anyways, we won't worry about it quite yet. So the 3 sum is going to be the sum of these 3 things. Okay, and now we have to handle those 3 scenarios. If the 3 sum is equal to 0, then that means we've actually found one of the things that we want to add to our solution set. We can say res.add. And I'm going to use a tuple for this because, again, things that we put into a hash set have to be hashable. Lists are not hashable, so we'll store them as tuples for now. So we'll add in value, nums left, and nums right. Okay, and assuming that we actually did get a match, now we can move left inward, and we can also move right inward for the reasons we said earlier. Okay, and I'm going to say now else. So assuming we didn't get a match, one of 2 things will happen. Either the sum was too small, so less than 0, or the sum was too big, so greater than 0. So one of the routes here is if the 3 sum is less than 0. In this case, we want to select things that are bigger, right? And this means that our left pointer is going to move over by 1. And then, just for the sake of clarity, so we could have just said else here, but I think, you know, just for the sake of clarity, I'm going to say now if we had a positive number, then let's move the right pointer inward by 1. Again, because that's going to make the overall sum smaller, which means it's getting closer to 0. Okay, that I think is the overall logic here. I'm trying to think if there's like any edge cases that we missed or anything like that, but let's see how that did us for. So by the time we get to the end, we're going to return. So right now we have a set of tuples. What we want to return is a list of lists. So I'm going to do a list comprehension here where I say convert the tuple to a list for each tuple in res. I almost definitely messed something up there, but we're going to find out, you guys. This is part of the beauty, is you can make mistakes in your interviews, as long as you're smart about fixing them. Oh, I forgot to sort. Off the bat, I'm looking at this and I went, hey, that's not sorted. I thought it was going to be sorted. Okay, so we'll say res.sort, and then we'll give this another shot. Ooh. Let's take a look. Not res.sort, nums.sort. Yeah, that's what I wanted. Oh. Is this going to work first try, guys? Well, not first try. Okay, well, we got to submit, which is, you know, that makes me happy. That feels really good. But there's still some things we can do to optimize this. So we're not done. Can I see what you returned? No. Guys, we're going to wait till Sid leaves, and then I'll show you guys what I returned. Okay, so right now, at the beginning, we create the set, and then we put a bunch of tuples into it because they're hashable. At the end, we need that set of tuples to become a list of lists. So the outer part here is I want to return a list, and the inner part is go ahead and convert those tuples to a list. Or what's the word? Cast the tuples as a list. Okay, so what can we do better here? I have a few thoughts. One of them is, since the numbers are sorted, let's say we were just looking at this. Let's say this was our array right here. We're guaranteed, well, okay, actually, let's even take a step further. Let's say this was our array right here, just 1 and 2. There's no way for us to get a valid triple here because they're positive numbers, and there's no way you can add together positive numbers to get 0, right? So we can actually stop this early because as soon as we're looking at all positive numbers, there's no more answers for us, right? So at the beginning here, we can actually say don't even do all this if the value is already greater than 0. So if we do this, then forget about the rest of the array. We're done looking, skip to the return statement, right? We could do a little bit of like guarding to say like, hey, we're never going to have to do this when we're within 3 elements of the end of the array, or like 2, you understand what I mean. So if we only got 2 elements left, we don't have to do this, but that's going to break really easily anyways, or like it's going to end very easily anyways because of this part right here. So I don't know if it's worth writing an extra piece of code just to save us like one very quick loop in the future, right? So we'll just leave that as is. But what else? What else? We could also say, so like when we do this, let me zoom out a little bit here. If we've got a bunch of numbers in a row here that are all the same, so for example, when we get here, once we find a match here, and let's even illustrate this more. Let's say there were like 6 negative ones in a row. Yeah, so let's say there were a bunch of negative ones in a row. We don't need to look through all of these, right? Like it's not helpful for us to do this. As soon as we find a match where we have, the red is a -1 here, we're gonna find all the combinations that use these, right? And then when we shift over, it's gonna be the same combinations and the same combinations and the same combinations and the same combinations. So another thing that we can do here is we can say actually, let me think about this. If the thing we're currently looking at is the same as the last thing we looked at, so like we don't need to resolve with the same first number, right? Because we've already, by the time we're done with that loop, we've already found all the solutions for that first member of the triplet. So we can say if the current value we're looking at is the same as the last value we looked at, then don't bother looking through the rest of the array. Just move it over until you get something new as the first element, right? Because again, we don't want dupes. So that's another thing we can do, except this is going to start at 0. So we don't want to check this if we're looking at the very first element of the array. So if index is greater than 0 and this works. So this is going to like make sure that we don't try and access something in the array if there's nothing before it. So the first time we won't do it, every other time we will do it. Okay, and if this isn't gonna like mean anything to you guys, but we submit it and it hopefully works again. Yeah, so I promise it's faster. There's probably a bunch of other like micro optimizations you could make if you have good information about the data. Like for example, if it's mostly negative numbers or mostly positive numbers or it's a lot of zeros, you might do some things to quickly look through the data. So like, for example, we could right off the bat, before we even do anything up here, when we sort it, we could say like if nums 0 is less than 0 and the last element of nums is less than 0. So if it's all negative numbers, what the hell are we doing? Just return an empty list because you can't add together negative numbers to get 0. Or if num0 is positive and the last entry of nums is also positive, yeah, then we can just return the empty list. This is probably, okay, just in terms of code style here, since this is going to work fine the way it's typed, but I think it's probably better for us to say, let's wrap this in parentheses. Oop. And then put these conditions on their own line. So this is like one condition if this and that, or if this and that. So it makes it a little bit cleaner to read. Then we'll return the empty list. And then this actually we'll put on the next line. This is also really helpful for Python since indentation matters. Like this is a nice way to put it so that you can guarantee you're in the right place for this line. Okay, and again, let me just run this to make sure I didn't mess anything up. Okay, yeah. So micro optimizations, we won't go over like more of these because they're very situational. But if you have extra time in your interview, this could be a good thing to do. We could say, hey, there's actually some special cases that we can return early for. So if it's a shit ton of data, but it's all negatives, we get to very quickly skip it, right? Um, so yeah, as we talked about before, if you have the extra time, it would be a good idea to talk about your time complexity, which we said was O of n squared here. It'd be a good idea to talk about optimizations you can make. And if your interviewer has recommendations for you, like what if we used this data set, or what if we didn't use this data structure, or maybe, like this part of your code seems like it's slower than it needs to be, those are things you want to listen to and definitely address. But this was so much smoother than yesterday. Whew, it's a sigh of relief for me. Um, Anybody have any questions? Anything I can explain more, or something that you think could be improved here? A question that I could answer for you? Okay, if there's no questions, I'm going to expect every single person in this meeting right now to have a solution posted in the text thread for this problem. Someone left. Someone left. Anyways, I highly recommend it. You've learned the solution now? More, I'll teach you later. I will teach you later. If you need more help on this problem, if you can't solve it on your own, ask some questions. We're here to help. We got the solution here. I'll post this recording, I think, later on tonight. So if there's anything I can help with, let me know. But I'm looking forward to seeing you guys' solutions. Hopefully you'll be able to figure it out on your own. Sweet. Thanks y'all for joining. And again, let me know if you have any questions, but otherwise, I will see y'all tomorrow night.